Ghost Riders in the sky.
Hello, welcome to the Emperor's Armory. Welcome to another video. So in this video I'm going to cover the Ghost Grid. Now what's that about? So typically in RTS games, and that's what we're building here, typically in an RTS game you have quite a lot of pathfinding that goes on. And pathfinding for your units, moving them around from point A to point B, is a big deal. Bad pathfinding in an RTS is like having bad graphics in an FPS game, a first-person shooter, or having like bad physics in a first-person shooter, or bad physics in a racing game. Like this is one of the core essential elements of the game. So pathfinding in the game that we're building is absolutely essential. And there's different ways of handling pathfinding in RTS games. Typically, Command and Conquer. Here's some Command and Conquer. They pioneered, this team here, Westwood Studios, they pioneered some of the early RTS pathfinding systems, and there's some fascinating videos on how they did it. And they did a very good job for back in the day. Yeah, even by today's standards, it was still pretty good. But if you ask anybody from that time, they'll tell you that it wasn't perfect. There was plenty of mistakes, plenty of inaccuracies about how their pathfinding operated, and it could look pretty annoying at times, especially if you're in a competitive match playing against somebody and your units go off in the wrong direction. That's super annoying. So then you've got StarCraft 2, and these guys really have probably, I suppose you could say that they've really perfected pathfinding for RTS games. I don't think there's any other RTS that probably has better pathfinding than what they've got. But I do know for a fact that they use a sort of hybrid A-star for their pathfinding, which is great for relatively small numbers of units, but is not great for very large volumes of units doing a lot of things. A-star breaks down in large numbers. So then this game here is Supreme Commander, and this is obviously hundreds of units. I think there's actually thousands of units. I think I've seen somewhere that they can handle up to something like 50 players all at the same time. So that's a tremendous amount of units all doing pathfinding all at the same time. I don't know what they use, but this is analogous to what we're going to do in our game. So our game is based on the Great War, World War I, and as a result, we need to be able to handle large volumes of units doing pathfinding. So using something like A-star is out of the window. We can't do that. So we're going to use vector field pathfinding. And I've actually already built the vector field aspect of it. But what this video is about is the underlying data structure that we're using in our game is a quad tree, a spatial accelerator. And there aren't really too many tutorials on how to do vector field pathfinding inside a quad tree. So I'm not going to produce a full tutorial, but I mean there's like almost nothing like whatsoever. There's a couple of papers. There's one paper from back in the 90s about how a team of guys did vector field pathfinding inside a quad tree, and how but it mostly focuses on how they hacked their GPU to do this, and how they achieved absolutely incredible performance out of it. And that was back in the 90s. So I couldn't find any videos about how to accomplish vector field pathfinding inside a spatial accelerator, inside a quad tree. So that's what this video is about. I'm going to skip over quite a lot of details, like how do you actually perform vector field pathfinding, how do you perform wavefront propagation or a range search inside of a quad tree. I'm going to skip over all of these things because any one of these is a huge subject which would take hours to go over in proper depth. There are lots of other videos about these, and they're relatively well covered subjects, so if you want to know about those things, there's plenty of other resources. I'm not going to double over because it would be outside the scope of this video. Anyway, so that being said, let me jump into the diagram. So this being the Emperor's Armory, of course, I'm a huge fan of Warhammer 40,000 universe, and it comes out in the art, it just oozes grim darkness, because I like that. Anyway, so okay, here we go. So yes, the quad tree vector field pathfinding. So let me break down what the problem is, why you can't just use standard vector field inside a quad tree. So here you have vector field pathfinding with wavefront propagation, and here you have a kernel. And so when you're performing the kernel search, or when you're performing the pathfinding through this standard 2D grid, you have your kernel, and you pass over every single element or every cell inside the grid. And every time you're on any particular cell, let's go to the target cell over here. When you're on the target cell, or any cell, you have to search its neighbors. So for every one cell that you go through, you also then have, you multiply that by 8 for its neighbors. It's a bit different around the edges. There are fewer, but on most of them have 8 neighbors. And then that gives you the number of actual operations that you're doing eventually. There's different layers of operations. Not all operation is as intensive as every other operation, but you do have every cell. So this is a 25 by 25 grid, and I think that's something like 650 cells, can't remember. So then you would multiply that by 8, which I can't remember what that is, like 2,000, no, I can't remember, 3,000 something. Anyways, the point is that here you have the standard grid, and you have to stop at every single cell, and then you use the kernel on every single cell, and you end up with a huge number of operations. I'm saying that like you've got a huge number of operations. When we've been testing this in our machines, the team and I, we're getting really high performance. Sure, it's only 25 by 25, but when we run this pathfinding with the wavefront propagation and vector field, it happens almost instantaneously, and so there's really, really low latency, and this is great. However, this depends on the fact that you have a standard XY grid. Well, we're not using a standard XY grid, we're using a quad tree. So now let me show you using the kernel inside of a quad tree. You can maybe already see the problem here. So here is the first element inside the quad tree. Okay, it's got no neighbors on these sides, that's fine. It's got these cells down here, and these cells, or these nodes, are the same size as the node that we're checking, so that's fine. But when you come to this node here, and you're checking its neighbors, well, these neighbors are the same size, this one is the same size, but this neighbor over here, this is a different scale, this is a different resolution or size of neighbor. So all of a sudden, where you've got a kernel, where every cell inside of the kernel for neighbor checking is the same size, then that doesn't work inside of a quad tree. And in fact, this quad tree that you're seeing here is in Cartesian perspective, but if you look at it in isometric perspective, it's not even a two-dimensional data structure. It's actually a three-dimensional data structure once you add in the branches. This is just a two-dimensional representation of that. So you can't use a two-dimensional kernel to search a three-dimensional space. It breaks pretty quick. So hence why, yes, we've got the vector field pathfinding with wavefront propagation working correctly inside a 2D grid, but we're not using a 2D grid, we're using a 3D grid, or we're using a spatial accelerator in the form of a quad tree. So okay, so let's move on. So this is actually what the game kind of looks like, or the way the data is currently structured. So we've got the root, the branch, and the leaf. Obviously it's inverted, but I just find it a bit more intuitive when the leaf nodes are at the bottom because it's the highest resolution. Anyway, so this represents the terrain tiles that we have. And you can see in this quad tree over here, there are sections of the quad tree that are empty. Nothing, nothing, empty, 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 and there are leaf nodes, but not every single cell over here has a leaf node. Well, actually, our quad tree has something in every single leaf node. So actually, in effect, we actually do have a standard grid at the leaf level. So then I suppose that leads to the question, well, if you've got something in every single node at the leaf level, and if it actually technically is a standard grid at the leaf level, then why even bother with a spatial accelerator, a quad tree? Well, that leads on to the next thing over here, which is the quad tree's range search. So in the range search, let's just say effectively starting position, ending position. Oops, I'll just change that up. So the starting position and the ending position is effectively like going from this cell over here to this cell over here. And as you can see, when we go from here to here, we can ignore this quadrant and this quadrant and this. There's loads of quadrants that we can simply ignore. And the reason that we can do that is because you start the search at a high level, and if at a high level, if you can see that an entire quadrant is empty, then you ignore that quadrant. You ignore that quadrant, and when you ignore it, you're also ignoring all of its children. So even though, yes, technically we do have a full grid at the leaf level, because the full grid is actually part of a quad tree, when we perform the range search, we ignore huge quadrants, huge swaths of the area, and we just pretend like they aren't even there for the sake of the range search. Okay, so here we've got starting position, ending position, and then every cell that you come in contact with along the way from starting to ending, and then you ignore the rest of them. Okay, so that's the range search, but how do you actually do the vector field pathfinding inside this? Because this doesn't actually do any pathfinding. If you have obstacles, this doesn't go around them or anything like this. It just tells you which cells are involved. And this is over here is a, oops. This is a more conventional diagram for what a range search looks like instead of a quad tree. Okay, so here is the next step. You have some sort of data structure, and inside that data structure, once you've run the range search, you collect the cells which exist in the path that you're going to need for the path from point A to point B, or starting to ending position. You collect all of those cells into some sort of data structure, and then you create the ghost grid. So the ghost grid has the proportions of a standard grid, and the proportions are generated on the fly. And this is the great thing about the quad tree, is that when we're doing the vector field pathfinding inside this system, we are only ever actually moving from one small part of the map to another small regional part of the map. It will be unusual to go from absolutely one complete far side of the map to the other far side of the map. Most of the time it will be small regional movements that happen. So we can generate the pathfinding field on the fly. We don't need to cover the entire map when we do it. And so this is what the ghost grid is about. So let's get into the ghost grid. So here is the start and the finish. The width of the map, the number of columns, is based on the horizontal distance between the starting and the ending positions. The height, or the number of rows, is based on the height distance, the difference between the starting and ending columns. And that gives you the height and the width of the ghost grid, the rows and the columns. In this case there is an 8 by 8, but it could be anything. It could be whatever your range search comes up with from here to here, starting to finish. That is the size of the ghost grid, which gets generated on the fly. So okay, so what is the ghost aspect of the ghost grid? Well, here you have the dictionary which you collected, or sorry, here you have a collection of the elements that you've got that you picked up from the range search, and these represent the cells, the elements in the leaf node. So you've got that. You've got the selection of the cells which you need to go from point A to point B, but you still have the structure of the whole grid. Well, the trick now is that when you perform the kernel, you can still perform the kernel like standard, because the kernel has a standard size grid inside of it, and the grid itself is a standard size now. So you perform a standard kernel search and it operates perfectly, even though this was extracted from the quad tree. Because you've got this grid structure where every cell, every row, every column they're all equal to each other, a kernel now operates correctly inside of this. And so this kernel, in conjunction with the cells which exist, this gives you a huge amount of selectivity over which cells you're going to perform the search on. So in this cell, this first starting cell, you'd go to it and then you'd say, does something exist at this node? And yes, it does. Okay, so now perform a neighbor search. Nope, 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 nope. Yes, something exists inside the cell. So now you run the pathfinding using this cell. Then you go to the next one. Nothing here. Nope, 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 no, 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 no. You come to here. Does something exist at this cell? Yes, it does. Okay, so now use the kernel and perform the neighbor search on the neighbors of this cell. Yes, it does. Okay, now you can perform the pathfinding based on this existing inside the this data structure. And nope, nope, nope. Okay, perform the search. Nope, nope, nope. So what you can see here is that because there are huge sections of the ghost grid which are empty, although you do have to iterate through every single element in the ghost grid, you only have to run the heavy vector field pathfinding. Well, I say heavy, it's only relatively heavy, but you have to run the vector field pathfinding on only selected cells which exist based on the range search inside the quad tree, which is then produces this data structure of existing cells. And then these existing cells are the only ones that you run the vector field pathfinding on. So in this 64 cell grid, 8 by 8, I don't know what 8 times 64 is, but that's approximately how many elements you would have to stop on and perform this if it was a standard grid. But instead of performing an 8 times 64 searches on every single element in this grid, instead we've only got 8 elements inside this grid, and so we're only performing 64 searches. Or only 64, we're only running the vector field pathfinding 64 times with each of the 8 neighboring cells and each of the 8 existing neighbors, which is that's way fewer. We've managed to cut out entire chunks out of the entire quad tree. So I know this is we're only showing small numbers here, 25, 8 by 8, whatever. These are just small numbers. But imagine that you've got a map which is thousands and thousands of cells wide, or hundreds of cells wide, and you've got tens of thousands of units that are all moving around, all doing something. Well, we can ignore the vast majority of those elements and cells and agents within the game when we're performing a search from one position to the next. So yeah, using the range search in combination with the ghost grid gives us this huge advantage to be able to only pathfind through cells which exist in the path that we're taking. And so effectively that would be like, here's some agents. Let's put some agents on here, a couple of agents. Okay, so here's a bunch of agents, and let's say they're over here, and obviously you want them to go towards the target. Well, you can see the arrows pointing their path, how they get to here, except that you can see that we don't have anything happening over here in this quadrant or this quadrant. There is a bit of something happening in this quadrant down here, but we would basically perform the vector field pathfinding basically only in about this much of the whole area. You would get to cut out all these sections over here, which is, this was already quite high performance when we were running it, and the quad tree as well is pretty high performance. There's no lag whatsoever. It's doing great culling, so we already have like really high performance. But it turns out that we're probably going to be able to improve the performance even more by using wavefront propagation through the vector field, which wasn't my intention. I just wanted to get it to work, but it turns out that we're actually going to even optimize the speed, which is already pretty fast. There's different things that we could do with that new speed that we can crank out. The one thing would be we could increase the number of units that a player can play with, but I think we're going to be careful with the number of units that we use in the game, because it can end up turning into a bit of a chore, and it can become overwhelming for a player if they have too many actions that they have to perform at any one given time. So we will probably use quite a few units, but we'll have to watch it carefully to see that players are not overwhelmed, and that they're able to do micromanagement and macro management, and that the number of units that they're playing with is a fun number of units. We don't want to overwhelm the player. So yeah, there we go. There is vector field pathfinding in a quad tree with plenty of grimdark art, and so I hope that was interesting. I know there aren't really too many videos out there covering how to do this, or I couldn't find any videos at all about how to perform exactly this type of search inside a quad tree. So I hope that's useful for anyone who's watching it. Please like, share, subscribe. I don't know when the next video will be out, but whenever it is. Hopefully the game will be a bit further down the line, we'll have a bit more to show on the game. So thank you very much for watching this, and I look forward to seeing you all the next time. Thank you again. Like, share, subscribe. Cheers. Bye bye.